All right, in this video, we're going to look at how to plot points in 3 dimensions, even though we're only drawing it on a 2-dimensional plane. So the first thing to keep in mind is that in mathematics, we generally use what's called the right-hand rule. There is a corresponding left-hand rule that you will sometimes encounter in other fields like physics, but in mathematics, we generally use the right-hand rule. And basically, the right-hand rule is created by your right hand, as shown in the picture. So if you have your first 2 fingers, your index and your thumb, pointed like a gun, and then you point your middle finger out at a 90-degree angle from the palm of your hand. This creates 3 axes, and the X, Y, and Z axes are going to follow this pattern. X and Y will be your 2 fingers, and then Z is your thumb. Typically, the way this is going to appear on paper is in one of these 2 drawings here. So I'm going to primarily be using X coming out of the paper with positive Y to the right and then Z pointing upward. But I have also seen other people, particularly in some textbooks, although the one that I'm going to show you with the A version, that is very common in textbooks. I have seen some textbooks keep the XY plane on the paper and then Z come out of the paper. But it is more common to have Z pointing upward. And so that's the version of this that I'm going to use in this demonstration. All right, so the best thing to do, though, anytime you're using any kind of 3-dimensional coordinate system, is because there is more than one way to do this, you should always, always, always label your axes. In the 2-dimensional plane, there is always X pointing to the right and positive Y pointing up, and there's no deviation from that generally outside within mathematics. That is the standard. And so if you don't label them, people assume that they are that way. But because there is more than one common way of doing this in mathematics, it is always a good idea to make sure that you label all your axes. It's very easy to misinterpret 3-dimensional anything in 2 dimensions. And so it's always a good idea to just require all the axes to be labeled just for the sake of clarity. Now we're going to start by plotting a point. I'm going to pick one that's in the first octant. So that means all of the points are positive. And then we'll plot some other example with another point in another octant of the graph. Now, the first thing to kind of keep in mind when you are drawing a point in 3D is that, particularly in this standard orientation, X and Y are in perspective. So we are not looking at an actual right angle on the paper. X, Y, and Z have a right angle on the paper, but the angle between X and Y is not a right angle on the paper. And so one of the issues that this tends to cause is that students will try to impose right angles onto the XY plane, even though they're looking at it from an angle. And so that's going to make your graph look really weird. Instead, what you want to keep in mind is that your coordinate axes are going to guide your grid axes in other directions. So your Y coordinate tick marks are going to be in parallel to the X axis. And if you are in the going in the X direction, these tick marks should be parallel, these grid lines should be parallel to the Y axis. And so what you should do is you should imagine, again, drawing these in parallel. Now, when they're in the 2-dimensional plane, the XY plane on the paper, these will form right angles, but these will not form right angles. These will form little parallelograms on the axis in the perspective view. So it's important to keep that in mind. Draw your tick marks, draw your light lines as you go through these tick marks in parallel with your x-axis to make them line up nicely for you. And then the first thing to do is to plot your point in the plane first. So don't worry about the z-axis and the xy plane at the same time. Just plot these first two coordinates, x equals 1, y equals 2 in the plane. And so notice I've drawn 2 tick marks here in the y-axis to correspond to our y direction, and then only 1 unit tick mark out in the x direction. And my x grid line is parallel to my y-axis, and my y grid line is parallel to my x-axis. And so where they intersect is that point 1, 2. Now, from this point, you're going to measure up 3 units. Since we're plotting the point 1, 2, 3, we're going to measure 3 units up in the z direction. But because, again, keep in mind, we're in perspective, we're kind of looking at this from above the plane, we're not going to be able to plot the point directly 3 units up on the z-axis, so like up here someplace. That's not correct. We have to start this 3-unit climb from the point in the plane that we plotted, again, to account for that perspective. And so what that's going to look like is this. So I took my 3 units that I had climbed up in, I had measured up in the z direction, and starting from that point 1, 2 in the plane, I then counted up from there. Now, when you're drawing points in 3D, if you just, sort of eyeball this and you plot it, it's not going to look like it's at the point 1, 2, 3. So it's often a good idea to use your tick marks and to draw this vertical line up from the plane in order to show that 3D perspective to, again, help the viewers understand like where this point is coming from. Because the graph is static, that 3 dimension is really lost very easily. If this was something we could rotate, maybe we wouldn't have to include these elements, but being able to plot it like this, especially one point at a time, including this grid information and the vertical step up from that point in the plane, really helps make that feel like it's like on the edge of a box, as opposed to just randomly sitting on the paper. It could be anything. So that helps make it clear. So let's try another example, and let's include some negative values in here. Now, if we're plotting the point -2, -4, -6, we're basically going to be plotting behind the octant we were just plotting in. So we were originally plotting here in this first octant with positive z. So in this top 1/8 of the graph. But now we're moving everything into the background. So the grid lines are basically going to work the same way. So again, when we go out in the x direction, instead of coming away toward us on the paper, out of the paper, we're going backwards through the paper. So we're going 2 units out this way. And again, that line coming off the x-axis should be parallel. The tick marks aren't really as important, but the line, the grid coming off of that axis should be parallel to your y-axis. And that tells you how far back on the x-axis you're going. And then on the y-axis, again, we tick mark out 4 units, and then that line, that grid coming out from the negative y-axis, in this case, 4 units. Again, the point in the plane is where those 2 lines intersect, and this line is, again, parallel to that x-axis. So that's how we handle that perspective. And then we're going 6 units down in the z direction, but this measuring it on the axis just gives us like how long that unit, how that length is. And then we move the starting point to where our point in the plane was, our -2, -4, and then we drop that down. That's 6 units from there. And so again, including this information with the point in the plane and the vertical line connecting the point gives us a little bit more of that perspective view so that we can identify, yes, this is that point, -2, -4, -6. Now, we're going to talk very briefly about doing this in cylindrical and spherical coordinates. Now, some textbooks will cover this information very early in multivariable calculus, and some textbooks will save particularly spherical coordinates until like you have to use it right away in multivariable integration and triple integrals. But again, the cylindrical coordinates is basically just polar with a z-axis, so that should be clear. And that's actually the easiest to plot after rectangular coordinates. Rectangular coordinates, there's a nice sensible feel to it that you can replicate all the time. And sometimes if you're plotting points in these other coordinate systems, it may be more useful to replot them in rectangular coordinates. Just because rectangular coordinates is there's a nice mechanical way of plotting them, but we're going to look at both of these other versions. Now, in the cylindrical coordinate system, you basically have, again, the same axes. You've got X and Y and Z, but now the X-axis is your theta equals 0 line, and in the plane, this is your R theta point. So R is your distance in the XY plane from the origin. Theta is your angle between the positive x-axis and your line, which is where your radius is. And then Z is just plotted vertically upward from there. So again, you can imagine this kind of being like radius equals 3 and theta is maybe pi over 4, and then Z is maybe 2 or something like that. Just moved up from the plane. Again, you kind of have to keep in mind you're in perspective, and so your angles are not going to be exactly what you would imagine they would be on just drawing a 2D grid on the paper. When you're doing like a pi over 4 angle, which is like halfway between the axes, you kind of have to eyeball it as to like what is halfway between the axis in this perspective. And so it can be, again, a little bit challenging to do by hand. But most of the time you're going to be asked to plot points, it's going to be in the rectangular system. And then in the spherical system, the thing looks like this. So theta is the same. So this is the positive x-axis, and the theta is your angle from the positive x-axis to where your rho essentially projects onto the xy plane. And then your phi angle is the angle from your positive z-axis to where your rho vector, your rho length actually is. And then rho is the distance itself from the origin to the point in 3 dimensions. So what I plotted here, this is the R distance from our cylindrical problem, and this is the Z distance from our cylindrical problem, essentially. But the way that we're plotting this is not in terms of rho and Z, or R and Z, but it's in terms of rho and phi, and the theta is the only one that's the same. So again, this can be quite tricky because you're not really plotting rho. I mean, technically, it's not even on the plane. It's out pointing in space, and so that can be a little bit harder to visualize. And so there may be some advantages to, if you're trying to plot a spherical coordinate point manually, to actually do the conversion either to cylindrical or to rectangular in order to better get it plotted in the exact point that it needs to be.